So in this chapter, we are introducing measurements and estimating and unit conversions as well. So this is the number 1 chapter for your course. So let's begin. So what are the chapter goals? Basically, we'll introduce physics as an introduction, explain the difference between a principle and a law, physical quantities and units, accuracy, precision, and significant figures, and approximation. But before we get into the nitty-gritty of these estimations and significant figures and other concepts, let's talk a little bit about why physics is necessary. So when we look around, the physical universe is enormously complex in its detail. Every day, each of us observes a great variety of objects and phenomena. Over the centuries, the curiosity of human race has led us collectively to explore and catalogue a tremendous wealth of information, from the flight of birds to the color of flowers, from lightning to gravity, from quarks to cluster of galaxies, from the flow of time to the mystery of creation of the universe. We have a lot of questions, and we want to know how these things come into play. So it is the underlying order of nature that makes science in general and physics in particular so enjoyable to study. For example, what do a bag of chips and a car battery have in common? If we start thinking, well, both contain energy that can be converted in other forms. So you're basically studying the laws of energy, the law of conservation of energy, basically, which says that energy can change forms but can never be created or destroyed. So we are very much wanting to learn these phenomena behind the unifying aspect of physical laws and the basic simplicity of nature from the underlying themes of this text. So from the text that you're going to learn from the textbook, in learning to apply the laws that you'll learn, and of course study the most important topics in physics. For example, this entire course is based on mechanics. So we'll be talking about Newton's laws, gravity, conservation of energy, conservation of momentum, and rotational motion. So in order to get into those chapters, the very first thing that we do is learn to handle quantities, handle numbers, and that is why chapter number 1 is very important. That is why we train ourselves. How are we going to write these numbers? There should be a common code, common law. We can't randomly write large numbers. We have to reduce them, shrink them to a scientific form so that we can read them easily. If I have to write a very large number, it will be very hard for me to read. So that is why we have scientific notation. And if you perform calculations and then your calculators spits out a huge number, you can't give me the answer with all that entire number. So you have to learn where to cut that number. So you have to learn about significant figures, and then you have measurements to be done, which are in if centimeters need to be converted into meters or meters need to be converted into centimeters. That's why you need to know unit conversion. So this is the significance of this chapter, and it's a very important chapter if you have to smoothly go into other chapters where you will require these tools, basically. So physics has developed out of the efforts of men and women to explain physical environment. I agree. And what does physics encompass? A remarkable variety of phenomena. We want to learn about planetary orbits. Basically, where are these radio waves and TV waves coming from? Unfortunately, your chapter will not be dealing with this. This is part of chapter 2, physics 2, not chapter 2, physics 152. So here we only deal with physics. 151 is only about mechanics. So this is just an example. And physics is Physics predicts how nature will behave in one situation based on the results of experimental data obtained in other situation. Newton's laws are responsible for rocketry and Maxwell's equations. If you are going to go for calc-based physics in future, you will learn how important Maxwell's equations are for telecommunications. Basically, physics 172 uses Maxwell's equations. If you are ever going to go up to physics 172, you will learn that it includes everything about electromagnetic waves. So next, before we get into the mathematical part of it, it is very important to know about phenomena like what is an observation. If these laws would not have come into play if we had not started the process of observation. Observation is very, very important. And then based on the observations, theories were developed, and a scientist, there were some smart guys who were observing. For example, Newton observed an apple falling, and he gave a theory, and these theories explain the observations, and observations will tell if the prediction is accurate, and the cycle goes on. You then conduct experiment. If the experiment comes close to theory, then the theory is valid. So this is the basic nature of science. So physics is the foundation of many important disciplines and contributes directly to others. It's not that physics is the only science that's important. Chemistry, for example, since it deals with the interactions of atoms and molecules, is rooted in atomic and molecular physics. So there is always an overlap. Most branches of engineering are applied physics. In architecture, physics is at the heart of structural stability. So you get into the civil engineering and is involved in acoustics, heating, lighting, and cooling. Let's not forget to mention that physics has many applications in the biological sciences. On the microscopic level, it helps describe the properties of cell walls and cell membranes. On the macroscopic levels, it can explain the heat, work, and power associated with human body. You are measuring blood pressure. It has physics in it, and physics is involved in medical diagnostics. What could have we done without X-rays, magnetic resonance imaging, which we call MRI, ultrasonic blood flow measurements? Medical therapy sometimes directly involves physics. For example, cancer radiotherapy uses ionizing radiation, and physics can also explain sensory phenomena such as how musical instruments make sound. I know that physics of voice and music is a very good course at Salem State University, where I used to teach many years back how the eyes detect color and how lasers can transmit information. So physics has vast use. I have justified how important physics is. It is not necessary to formally study all applications of physics. What is most useful is knowledge of the basic laws of physics. So if you are enrolled in a medical sonography program, having a sound fundamental knowledge about the laws governing the physics will be very helpful in future. So some students try to understand why they are learning physics if they have to go into medical field, but there is always an overlap, and having the knowledge of X-rays and having the knowledge of sonographic devices, there's physics behind them. So you will definitely be learning more and more about them if you are using them later, but having the fundamental knowledge is very important. So how does a new theory get accepted? Predictions agree better with data, and this explains a greater range of phenomena. So the more experimentation you conduct, the better will be your results. So physics and its related fields, I just described that it has a vast overlap with other sciences. And communication between architects and engineers, I was just talking about that. If the engineer who's working on the bridge does not have the knowledge of stress, strain, and other physics related terms, you can see the result here in this picture. A bad physicist or a bad engineer caused this. So what is a theory, what is a law, and what is a principle? A theory is detailed and can give testable prediction. A law is brief description of how nature behaves in broad set of circumstances, and principle is similar to law but applies to a narrower range of phenomena. So you will learn about this in your textbook. Go ahead and do your reading assignments. Every time you are watching these videos, you should first do the reading assignment. So basically, the laws of nature are concise descriptions of universe around us. They are human statements of underlying laws or rules that all natural processes follow. So the discovery of these laws is very important, and the cornerstone of discovering natural laws is observation. Science must describe the universe as it is, not as we may imagine it to be. So that's the underlying statement. So we go into the major portions that we are going to discuss here is measurement and uncertainty. You do the reading from your textbook for this portion. The PowerPoints and my lectures will not detail on the text part. The text is anyways always going to be detailed. So you should definitely work on your reading assignments. So no measurement you work on is exact. There is always some uncertainty due to limited instrument accuracy and difficulty in reading results. So if you're not measuring your readings correctly, you will definitely give a wrong data for maybe your job is to measure. You have to set a X-ray machine, and if you even make a tiny error, it can be a disaster for the patient if you are not sure about the measurement and you're not sure about the uncertainty that is there and what effect it will have on the patient. So even not only in the medical field but in everywhere else also, if you're not sure about the range of accuracy, precision, and uncertainty involved, you will not be able to give good results. And we all know that science is based on observation and experiment. Accuracy is how close a measurement is to the correct value for that measurement. For example, let us say that you are measuring the length of a standard computer paper. So you know that you have a standard computer paper, and the packaging in which you purchase the paper states that it is 11 inches long. So we have 11.0 inches long, and you measure the length of the paper 3 times and obtain the following measurements. So you ended up getting 11.1 inch. You did the readings 3 times, and you're not sure why it happened. 10.9 inches, and you can test this yourself. If you use 3 different rulers, or if you measure it 3 different times, or if 3 different people measure it, you will see that there will be range of values that you get for this one. Then these measurements would not be very precise because there would be significant variation from one measurement to another. So that's why it is important to know what is the accuracy, what is the uncertainty in the measurements. And then we will also learn about significant figures. Just as I was telling you that if you work on some mathematical problem and you punch it in the calculator, and you get a really large number like 2, 3.2, 1, 4, 5, 6, 7, 8, you have to know where you have to end this. You cannot write this entire thing because the calculator will not give you the significant figures. You have to do the rounding, and that's why you have to learn how to find the significant figures. We'll do a detailed work on this in the lab, as well as in we will have some examples towards the end of while I'm talking. So for example, let me tell you the significant figures here are 20, are 4. All of them are significant, but in this case we just have 2 sig figs. The 0 before the 6 is not significant, and in 80 kilometers it's ambiguous. It could either have 1 or 2 significant figures. If it has 3, it should be written 80.0. That means the decimal should be mentioned. Okay, so if it was written as 80 kilometers, generally we say that it is 2 sig fig. If it's written as 80 and it's an ambiguous thing, maybe they forgot to put a decimal, we can it will be correct to say it's 1 or 2. Okay, so measurement of uncertainty. How do we measure uncertainties? This is a very important part in the labs. Whenever we conduct labs, you are always asked to perform what is the percentage error that you got. So the formula for this is very simple. If your uncertainty is 0.1 and the actual value is 8.8, so you divide the uncertainty with the actual number and multiply it by 100%. Okay, and that gives you the percentage uncertainty. So we'll do some examples too. So now let's work on one of the example here. And what if I say that your bathroom scale reads your mass as 65 kgs with a 3% uncertainty? What is the uncertainty in your mass? So how are you going to solve this problem? So I would suggest taking a little break. You can stop my video over here and you can go ahead and work on this problem on your own first, and then start my video, and then you can look at the solution. It's always a good idea to solve the problem first yourself. So the uncertainty here is 3%. Okay, so 3% uncertainty, and I call it as let it be delta m is the uncertainty, and the actual value is 65. Actual mass is 65 kgs. In order to find we have been given percent, and this is the percentage uncertainty. You want to find the uncertainty. So in order to do that, there is a simple method. This is called delta m. You can also call it delta m, like this, as uncertainty. The percent uncertainty and the uncertainty are two different things. So you go ahead and you put this as 100% in order to find out the percent actual uncertainty, multiplied by 65 kgs. 65 kgs, and when you work on this, you get 2 kg uncertainty. So that means if you have to rewrite this number, the mass therefore is 65 plus minus 2 kgs. So there is a plus minus 2 of kg uncertainty in this mass. It can either be 67 or it can either be 63. That's the range. So next, let's take a look. If a car's speedometer has 5.0% uncertainty, what is the range of possible speeds when it reads 90 kilometers and convert this range to miles per hour. So this is a problem for conversion. Okay, we will look at more examples. This is just, I'm giving you an idea. So the car's speedometer has 5% uncertainty. Again, you'll do the speed. Let me denote the speed in uncertainty in speed as delta V, and that's equivalent to 5%. Same thing that we did behind in the previous problem, 100%, and multiplied by 90 kilometers. And I will write this as 90.0. Keeping all of them in the proper decimals, kilometers per hour. And when I work on it, I will get the uncertainty equivalent to 4.5 kilometers per hour. So the actual number can be written as the speed, therefore, is 90.0 plus minus 4.5 kilometers per hour. So it can either be 85.5 to 94.5 kilometers per hour. And this is the part A, and it has a part B as well, and which tells us convert this range to miles per hour. So now a simple problem of uncertainty has been converted into a problem of converting from one set of units to another, which we have not talked yet, but we are going to do this in detail. 85.5 kilometers per hour, and I have to convert it into miles. So the unit that you want on the top should go on the top. There's a conversion of 1 kilometer. 1 kilometer is basically equivalent to 0.6214 miles. Do not worry about the conversion numbers. I'm always going to give you the conversion. You just focus on how to do the conversion. So the kilometer and kilometer is going to go away, and once we multiply these numbers, you'll use your calculator and you'll see that we got the conversion as 53.1 miles per hour. Okay, and similarly, this is the lower limit, and similarly, if I convert 94.5 kilometers per hour into miles, using the same technique as I used here, I will get it as 58.7 miles per hour. So that means our range is between 53 to 58.7, while as over here we had 85 to 85 and 85.5 to 94.5. So this is how we do the conversions, but we will have tons of problems to do on this. I was just introducing the concept. So then there is another instance of an infant's pulse rate is measured to be 130 plus minus 5 beats per minute. What is the percent uncertainty? Up till now, you were converting from percent uncertainty to uncertainty. Now you're doing the other way around. You're finding the percentage uncertainty. So the actual number is 130 and the uncertainty is 5. In order to find percent uncertainty in this number, you simply use this uncertainty, which is we denote uncertainty as delta A. Over A is the actual number multiplied by 100%. If you go through your text, they have used the same formula, and delta A is represented by 5 and A is 130. So 5 over 130 multiplied by 100, actually I should write units, not, if you don't write units it has no meaning. Beats per minute, beats per minute. Do not forget units in physics. It has no meaning. It should automatically cancel to give us a number, because percentage error should not have a unit with it, but I have to show that it's canceling. And if you don't show the steps, you don't get the grade. Multiplied by 100%. So the percentage uncertainty, or the percentage error, is 3.84%. But since our it's one sig fig value, we always round to the value least sig fig that is given. The least sig fig is 1, that is 5. So we will write this as 4% uncertainty. Okay, so we will be doing extensively many more problems, and you can go ahead and again relate to the examples that are given in the textbook. When multiplying or dividing numbers, the result has as many significant figures as the number used in the calculation with the fewest number of sig figs. So when you're multiplying two numbers, the resulting number should have the significant figures of the least number that you're multiplying with. So this has 3 sig figs and this has 2 sig figs. The result in the end should have the sig figs of the least sig fig number, that is 6.8 in this case. And similarly, we can just do this quickly. How many significant figures are in 106.7? So anything beyond the decimal is also significant. So it has 4, this one has 3, and this one has 1, 2, 3, 4, 5. All numbers, even a 0 after the decimal, are significant. And in this case also there are 3. So very soon I will be teaching you about the rules, because we are very, very, very careful about the sig figs in our course. So now that you know a little bit about the significant figures, let me state the rules to you. Read from left and start counting sig figs when you encounter the first non-zero digit. So there are rules. There are 4 different examples that have been given to you, and all non-zero numbers are significant, meaning they count as sig figs. So for example, in this case you have 3 sig figs. In this case there are 6 sig figs, and now watch this. Zeros located between non-zero digits are significant. So the zeros in between 5 and 4 are significant. That's why it has 4 sig figs. The 0 in between 6 and 2 is significant. It's embedded in between. Hence it is a sig fig. So we have 3 sig figs. And over here also we have so many zeros in between. But since there is a 2 at the end and 6 in the beginning, all the zeros in between are significant. Hence there are 16 sig figs if you count them. Then the rule number 3, trailing zeros, those at the end, are significant only if the number contains a decimal point after. Otherwise they are insignificant, they don't count. In this case 5.640, just as I was giving you the example behind, the 0 is after the decimal, so that's why it has 4 sig figs. There is a 0, there's a decimal in front of after the 0, so all of them are significant, so we have 6. But here there is no decimal given, that's why we have 2 sig figs only in this case. Be very, very careful about these rules. And zeros to the left of the first non-zero digit are insignificant. They don't count. They are only placeholders. So for example, this one, the 3 zeros in front of 4 are not significant, because if I have to write them in scientific notation, we will come to that in the lab. We start walking from here, 1, 2, 3, 4. We walked 1, 2, and 3 steps. So 4.56 into 10 to the power of 4 minus 4. So we have 3 sig figs only here. And in this case, we have just 2 sig figs. The 0 in front of 5 is not significant. In this case also, all these zeros are not significant. We just have 2 sig figs. So I hope you get a good idea and you'll be ready for the other problems and homework. Then there is another rule. Rules for addition and subtraction is little hard. You'll have to pay attention to this. We are going to again take it in the lab. So this one is totally different from rest of them. So your calculated value cannot be more precise than the least precise quantity used in the calculation. The least precise quantity has the fewest digits to the right of the decimal point. Your calculated value will have the same number of digits to the right of the decimal point. So for example, you have 7.939. I would suggest always writing these numbers like this, one below the other, because addition and subtraction is little tricky. So you get 25.299. Okay. So if I round this to the closest value, it comes out to be 25.3. Now the rule is this has 3 sig figs after the decimal, this has 2 sig figs after the decimal, and this one has just 1 sig fig after the decimal. So when you round your answer in the end, you should round it to the value which is closest to the least sig fig after the decimal. That means there should be only 1 sig fig after the decimal. That is the rule. That's what it says. So when you round it, your answer should be 25.3. Okay, so least precise value, you're going to round to the least precise value. The least precise here is 11.1, not 6.26. So your final answer should match the least precise value. That's what it's saying. And rule number C is multiplication and division. It's very simple. You don't have to memorize too much with this. 27.2 has 3 sig figs. 15.64 has 4 sig figs. It's divided by 4 sig figs. Whatever answer you get, you should maintain it with the number which is the least sig fig. That is 3. 3 is the least sig fig. So once you write it down, this is the answer that is given by calculator, but when you round it to 3 sig figs only. Okay, so that's why we limited it to 230, which is 3 sig figs. Yes, if this was 5, we would carry 1 over here and write it as 231, but we don't have a higher value after the decimal, hence we round it to 230 decimal. Watch, we have written decimal after this. If I don't write this decimal over here, this will become a 2 sig fig only. So pay special attention to these rules. Then comes the rules for combined addition, subtraction, and multiplication division problems. So when you have a jumbled up problem where there's addition, subtraction, and multiplication, you should use the PEMDAS, which is use the multiplication and division steps first, and then addition, subtraction. So first apply the rules for addition, subtraction, and then apply multiplication and division. So if there's an addition and subtraction, go over here and follow the rule number B, and if there's multiplication and division, follow rule number C. So now we can just do a little practice. Provide the number of sig figs in each of the following numbers. So if we at this point, you should pause my video for a little while and go ahead and try yourselves first, and then after you get a good sense of what the answer is, you can go ahead and check what answers I have put. So in this case, we have 2 sig figs. In this case, there are numbers after the decimal, so all the numbers are significant, 1, 2, 3, 4, 5. And in this case, all the numbers are significant, 1, 2, 3, 4, 5. And in this case, 10 raised power 3 is not significant. It's the scientific way of writing a number. The significant figures are 3, and in this case we have a decimal over here, so we have 4 sig figs, and this is ambiguous. It can either be treated as 3 or 4, but normally we talk about this as 3 because there's no decimal after it. And then we come to units and standards and the SI system. I will now pause the video here and we'll go into part 2. I'll stop the video right now, and you should go over this material again and then watch the part 2 video.